This is Group 14, and welcome to our presentation. Software projects increasingly involve more AI-assisted edits, creating complex sequences of changes that are hard to follow. This project presents reproducible AI sessions, or for short, RAS, which is a system designed to record and replay these AI-driven edits. By capturing key steps and metadata of each change, RAS provides a clear, traceable history of edits. In this presentation, we'll cover it and how it fits in with Void, its use cases, and many more aspects and suggestions. Most development tools only show the final code, hiding the reasoning, intermediate steps, and AI-generated edits. This makes it difficult for developers and reviewers to track changes, understand why they happened, or reproduce them reliably on another machine. RAS solves this by capturing prompts, model metadata, file versions, and incremental changes in a structured, replayable format. Teams can inspect the full edit history, replay changes deterministically on any machine, and audit AI contributions, all without altering Void's layered architecture or workflows. By providing full visibility to the development process, RAS not only improves collaboration and onboarding, but also builds trust in AI-assisted programming, making it easier for teams to understand how the code evolves and confidently rely on AI-driven edits.
RAS is our main idea. Record AI-assisted edits so you can reliably replay them later. We add two small core services and a thin UI. The session journal is append only. It logs prompts, patches, and decisions. The replay engine checks the pre-image hash and applies patches automatically via bulk edit, with a dry run and a worker thread so the UI stays smooth. In the UI, a sessions panel shows a timeline, diff preview, and replay controls, with small diff zone badges in the editor. The config holds policy, recording level, redaction, defaults, and retention. Providers only emit model ID/parameters and content hashes, no secrets. Public APIs are minimal. It has a start/stop recording and then a replay, export, and import, so you can do whatever you want with the recorded sessions. This is a real dependency map from the code. Nodes are the subsystems, arrows show who depends on whom. Workbench plus text editor are the main hubs, where user flows go in and out. Core services are the mediator, while file system controller handles all OS access. Configuration fans out widely and connects to every different component. The AI lane is clean. Code edit to LLM message to tool manager to provider adapters. The adapters don't touch a UI or file system. This supports RAS as we added session journal besides LLM message to record prompts/patches. The replay engine plugs into core and uses bulk edit for atomic replays, and SEM only attaches to the bundles. Stakeholders emphasize different NFRs. Developers want low overhead and simple workflows, which points towards compact, easy-to-handle logs. Reviewers need deterministic, checkable diffs, so having a verified preimage plus exact patches matters. Security and compliance prioritize privacy, redaction, and retention controls, especially if prompts or streams are recorded. CI/DevOps require determinism for golden tests and reproducible builds, so stable, verifiable artifacts are key. In this context, option A, patch plus preimage, aligns with performance, simplicity, and reproducibility, while option B, prompt plus stream, emphasizes forensic depth, richer audit trails, and teachable replays.
For alternatives, we compared two main designs. The first one is deterministic patch replay. It's the simplest and the most lightweight, as it only stores prompts, patches, and pre-edit hashes. This keeps the storage small, privacy risks low, and the replay very reliable. The trade-off is that we don't capture any of the model's intermediate behavior, so we can inspect how the output was produced. The second option is full prompt and steam replay. This records everything, including prompts, model parameters, and full token stream. It offers maximum transparency and is useful for debugging or auditing model behavior. The issue is that it's much heavier and it requires larger journals, updated provider adapters, and stricter privacy handling, and is more sensitive to model drift. Overall, option 1 is practical, low risk, while option 2 gives deeper insight at a significantly higher cost.
The subsystems touched are Workbench UI, core services, configuration, LLM message service, provider adapters, SCM, and the file system controller. We had two core components, session journal and replay engine, and keep the style choices already there, layered architecture and implicit invocation via events.
RES preserves concurrency by keeping the renderer non-privileged and routing all edits to the core and main via asynchronous IPC. Edits are applied atomically using bulk edit service. Streaming remains smooth with backpressure and chunk grouping, and heavier tasks like hashing and diffing are offloaded to worker threads. This design allows multiple teams to work in a parallel safely, thanks to the IPC boundaries and type contracts across 5 vertical tracks: Session Journal, Replay Engine, Sessions UI, Configuration and Policy, and the SCM Attach Helper. Continuous integration practices, including the golden replays for deterministic verification and performance for micro benchmarks for journaling and replay overhead, ensure reproducibility and maintain responsiveness. Altogether, these measures enable safe parallel development while keeping Void's layered architecture intact.
This is our first use case, the AI-assisted editing via the edit command. The user runs/edit, the editor sends the prompt and context to the code edit service, which logs a prompt record and forwards to the LLM message service. The provider streams back, we log stream records, and assemble proposed diffs as a patch record. The user then accepts or rejects, and then that decision record is logged. On accept, Core's bulk edit applies changes automatically, and we can attach the bundle to the commit.
For the second use case, we have replay a recorded session on another machine. Replaying a recorded session is fairly self-contained. The workbench manages the UI and lets users upload a session replay. That session is stored in the session journal, and the AI session panel retrieves the events and replays them one by one until the user stops the session.
Here is our external interfaces. We store 4 record types: prompt, patch, decision, and optionally stream. Each one is a JSON line under void sessions. The core API is small, it just has a replay and verify preimage, plus the export and import helpers. Patch records are tied to a preimage hash, so replays are safe and deterministic. Stream chunks are hashed only, there's no raw content involved.
RES introduces several risks that must be managed carefully. Privacy is handled with local-only storage, redaction of sensitive content, and recording banner in the UI. Storage growth is controlled with retention policies and optional compression, while deterministic patch replay helps prevent inconsistencies from provider drift. Performance is maintained through asynchronous writes, streaming backpressure, and off-thread processing. Clear modular design, unit tests, and CI checks supports maintainability and correctness. Together, these measures ensure that the RES remains secure, reproducible, efficient, and reliable over time.
For our interactions and testing plan, we'll test how RAS plays with the rest of the editor: SCM/PR flows, terminal and debug, LSP completions, the chat edit service, provider adapters, and even config changes. Our game plan is run golden replays across different OSs to confirm the preimage hash and the exact diff. Do redaction checks by injecting fake secrets and making sure they get scrubbed, measuring typing latency and replay throughput so performance stays smooth. Stress it with faults, so do stress tests, and partial streams, user cancellations, and even hash mismatches so you can get every different possible problem. Finally, CI, or continuous integration, will dry run a replay on critical PRs so problems get caught before any merge.
Working on RES has taught us several key lessons. First is that clear, well-defined interfaces and modular services are essential for maintainability, testability, and safe parallel development. Second is trade-offs between complexity, privacy, and reproducibility must be carefully managed. Simpler approaches often reduce risk and performance overhead. Third is architectural alignment with existing layered structures, preserve stability while enabling new functionality. Finally, is that effective AI collaboration depends on clearly scoped tasks and human validation. The AI can accelerate drafting and analysis, but the team remains responsible for the correctness, validation, and capturing of trade-offs.
Lastly is our AI collaboration. We picked GPT-5 Thinking after comparing Claude, Gemini, and Copilot, and it was chosen for its multi-file architectural reasoning, not code generation. We assigned it 4 bounded tasks: the outline plus rubric, first pass architecture mapping, targeted dependency research to perform SAAM inputs, and suggested flow patterns for diagrams. We use short, role-based prompts tied to our A2 baseline, reviewed every output with 2 separate group members, and kept all data local. Overall, it did 20% of the work, while we did the other 80%. We owned the SAAM, use cases, diagrams, and then of course did any final edits. Finally, here are our references.